Okay, so we have seen the basic theory of category theory, yeah. So Yoneda lemma, then limits, co-limits and adjunctions. And one question that naturally arises from adjunctions is the following question, which is going to be its answer is going to be our topic for today. So suppose is an adjunction, how much of this adjunction can be described without referring to category D, or maybe or mentioning category D. This is the question. This is our motivating question for today's and the next lecture. So we know that there is a pair of adjoint functors, but then you are forgetting that D exists. So maybe there is a factorization of a functor, that's okay. But what do you remember if you have this? You have G and you have F. You only have a composition of these two functors. Okay, so we have T equal to GF from C to C. This is an endofunctor of C. And what else do we have? Well, we also have the unit of the adjunction. Unit has to do with just category C. Co-unit has to do with category D. Okay. So we have unit. So unit goes from which functor to which functor? Tell me. Nope. It's identity to GF. And finally, we have mu. Okay, mu equal to G epsilon sub F from TT to T. Okay, so epsilon sub F, like maybe I should write more about it, yeah. So, so mu is equal to G epsilon sub F from GF to GF. Okay, so this middle FG is being sent to this middle identity functor on D. You understand? And then we are writing the horizontal, like the vertical composition of functors and natural transformations. So mu is still a natural transformation, but it's going from GF to GF. Okay. So we converted the situation into entirely something related to category D. Okay, so we have this data, and this data can be written, so write this T equal to T eta from 1 to T and mu from TT to T. Okay, so this triple is called, yeah, the data T is called the monad induced by the adjunction F adjoint to G. Okay, this is not yet the definition. Yeah, I'm just, I'm warning you, I will give you a definition, but just having these natural transformations themselves is not really useful. We also need some properties that these natural transformations satisfy. But before that, please try to observe what we are talking about. T is a functor from C to C. So if we are looking at the category of endofunctors, like functor category from C to C, then this is just one single object. What is eta doing? Eta is a morphism in that category, but that morphism is from 1. Okay, so morphism from 1 to something, like if you imagine the same kind of situation where T is now a set, identity is singleton set, and natural transformation is a function, then what do you have? You have a set together with one particular element. Eta would be one element, and mu is a binary operation on T, because mu is going from Tt to T. So what is such structure called usually? Monoid, provided it satisfies certain properties. Yeah. Okay, so now this is not exactly a monoid. Of course, we are working in a different category, but they have to satisfy certain properties. So let me write certain properties of this. Okay. Okay, the data T satisfies, okay, the first kind of diagram that comes like this. Okay, from T to TT, can you suggest something? From T to TT and TT to T? What can be the arrow from TT to T? You just have to use eta and mu. This should be mu. Yeah, TT to T, that is just mu. Then this one is just 1 sub T. And this one, 1 sub T composed with eta. Not composed like the vertical composition. Yeah, so therefore we are going to say eta sub T. Okay. So this is true. Can you verify that? Why does this happen? Eta sub T. This actually follows from exactly triangular identities. Okay. Then another one is this, another horizontal composition, because there was another choice possible. So this diagram commutes, and this diagram, and then we will label these two diagrams as 1 and 2. And simultaneously it satisfies something like, I mean, can you understand what this first and second property is? It's trying to say that eta is left as well as right inverse. Right identity, left as well as right identity. And finally, we are going to say that mu is associative. And mu is associative, we write it like this. So TTT, TT, TT, and T. Okay. Okay, so here I am going to put mu sub T, then here I am going to put T mu, then obviously here I have to put mu and mu. So can you see what's happening? We are saying that apply mu first, associativity, exactly. Yeah, so associativity holds. So this diagram commutes, this diagram is number 3. So these 3 diagrams commute. So this data satisfies this property. Now, Obviously, I mean, whatever we have seen so far, that came from an adjunction. Now, here comes the definition. So, a monad T equal to T eta mu on a category C consisting of the data of a functor of an endofunctor T from C to C, then some natural transformation from 1C to T, and mu from TT to T, a natural transformation a monad T on a category consists of the data of this satisfying 1, 2 and 3. So just like we do with anything in category theory, we abstract out the properties of something commonly known, and then we play around with that. Yeah, so this is the abstract data at this point, and we are looking at the motivating example. Of course, came from one particular adjunction. Okay. So one simple example, as we already said, that this looks like a monoid. So a monoid should always give you an example of a monad. So for example, given a monoid M, then E and dot from M square to M. Okay. A monoid, I mean a set. We can define M cross blank as a functor from sets to sets. This is our T. Then what is eta? Eta should go from one subsets to, tell me, M cross blank. Okay. So what will be eta sub A? Eta sub A is a map from A to M cross A. What should it do? It takes an element little a and maps it to, you had to map it to E comma A. Very good. And what should be mu? Mu should be the multiplication of the monoid, but you had to do it properly. Yeah. So M cross blank to M cross blank. So mu sub A will go from M cross A to M cross A, which takes a triple M N A and maps it to Mn comma A. Yeah, you just take the action on this part. Can you understand that this is the free action of the monoid? I mean the free monoid generated by set A, M cross A. Yeah, you don't worry. A is never touched here. Everything that is happening is only happening inside the monoid. Okay. So given a monoid, define this functor, and this gives us, and this data actually defines a monad. So this is a monad on sets. Any questions here? Do you understand? Like instead of a monoid, you can also think of a group. So group action, it's a free group action. Yeah, nothing is really happening here. Okay. So naturally, once you remember this data coming from an adjunction, the question is, can you ask the question?
How do you recover the adjunction from the monad?
How do you recover the adjunction will come later perhaps. The question is, does every monad come from an adjunction? Okay. And the answer to this particular question, I mean, the concept of monad was being toyed with at that point. There were two independent answers in the exact same year. Okay, so answers, yes, of course, and both Eilenberg-Moore, I mean, these are of course two different names, but now we write their names together because they did it together, Eilenberg-Moore and Kleisli. Gave positive answers in 1965, both in the same year. But the interesting part was that their answers were not same. They had different answers for this question. Okay, so we are going to look at maybe let us first look at this particular example itself. Okay, so given this particular monoid action, which is free monoid action, can you answer this question in that case itself, in that particular example? Can you find another category such that an adjunction will give me this back? Before we try to understand what Eilenberg-Moore and Kleisli did. Well, okay, I will tell you how to do that. So,
Might be wrong, but we can construct a sort of like we have modules, so we can have kind of a
module, yes, exactly, modules over monoid, which are called monoid acts. Exactly, free module. A goes to the free module, so it's the free functor, free monoid act functor. And that's the forgetful functor. Wonderful. So that is the answer. So, for example, the monad from the above example is generated by the following adjunction. Okay, you are given sets on one side and then M sets on another. The category of modules is also the category of functors from a ring to AB. Yeah, we'll see that later. But this is like group sets, yeah, G sets. So it's the same thing, it's M acts. Yeah, that's the name. And then there is a functor, obviously. Let me call it FT. I'm referring to the monad T. And then G upper T, where this is given like this. So what does F upper T does? Well, F upper T takes a set and just gives me a functor. I mean functor from M to sets. What is the category M here? Can anybody recall it for me? one object category. Okay, others have forgotten. First lecture. One object category. So when I say a functor from a one object category, I simply have to give you one object of the target category together with action of, yes. Okay, so what does it do? It takes M cross A as the set, and then I have to give you the action of M on M cross A. So M cross A to M cross A. This is the action. It takes M comma N comma A to Mn comma A. This is the action. And GT, where GT is always taken from, let's say, the underlying set of the monoid act together with the action map, it simply forgets the action and it remembers B. So I will leave it as an exercise for you to verify that this adjunction indeed generates, it induces this monad T. Yeah, maybe generates is wrong, I should say induced. Induced by. The simplest possible thing is to see that given a set A, if you follow Ft, then you get M cross A, and you come back, then you get M cross A because it's forgetful. So that agrees with what your functor was, T. Yeah, that functor was M cross blank. Yes?
I did not understand what
Mm-hmm.
Ft of A is an object in M comma set.
M comma set. So it should be a functor, but that functor is nothing but an action of M. Object maps to object, and then every endomorphism gives you a multiplication, like scalar multiplication by an element. Yeah, so therefore I simply wrote it as a map. You understand this, or there is confusion? Okay. So this monad definitely came from this, and as you could see that this solution came from the free monoid act. So free and forgetful adjunction. Okay, so that was the solution of Eilenberg and Moore, the free and forgetful construction. So let us see that first. Okay, so our first answer is going to be definition. The Eilenberg-Moore category. I am just going to write EM, yeah, for this. Eilenberg-Moore category associated with the monad T, yeah, denoted CT, yeah, C upper T. This notation is really important. Has as objects. Okay, now pay attention what we are doing. Pairs A comma alpha, but alpha is a map from TA to A. Okay, so A is any object of where A is an object of C and alpha is any map from TA to A. Yeah, but it should satisfy something. Satisfying these two diagrams. Okay, you will understand what I am doing. A to TA to A. Of course, A to A, what should be the map? Tell me. Identity. TA to A, well, we are given this spatial data alpha, and A to TA, what should happen? Eta. Eta is already part of the data. Yeah, monad is given, so T, eta and mu are given. So eta is given. So what does this particular thing say? This is diagram number 4. What does it say? So this, okay, so the name for this is that A is an algebra with algebra operation alpha. Okay, so A is called a T algebra. A comma alpha is called a T algebra. Okay, so satisfying this property, and the second property is of course from TTA to TA and TA and A. So what should be the maps here? Tell me. Alpha, both of them are alpha. Very good. This is T alpha, and this one is mu sub A. What is this one trying to say? If you take multiplication on T, you do that first and then you apply the algebra operation, then that is same as doing alpha 2 times, which is our usual monoid action property. Let me remind you what that is. Like if dot is defined, yeah, M cross A to A is defined, and this M comma A maps it to M dot A, then what is this property trying to say? It's saying that M dot N dot A is equal to Mn dot A. And the first property is trying to say that 1 dot A is equal to A. Yeah, that is diagram number 4. And this is diagram number 5, where diagram number 5 is this. You have seen group actions, so monoid actions are similar, and these are the two properties which you want. So good. So the Eilenberg-Moore category associated with this monad has these as objects and what as morphisms. Well, let me say that. And morphisms and as morphisms from A alpha to B beta, yeah, the maps, I mean the morphisms F from A to B satisfying, well, the obvious diagram, like TA to TB and A to B. What do we have here? Map alpha, then we have map beta, and here we have TF, and here we have F. This is our diagram number 6, and what does it represent? It says that, okay, I will answer your question in a minute. It says that, I mean, F of M dot A is equal to F of M acting on A. This is what diagram number 6 is trying to say. Okay, your question was that what is its connection with algebra? Now think about, let's say, category of groups. Does there exist a free forgetful adjunction to category of groups? Yes, given a set, you can construct the category of groups, like a free group and then forgetful functor. Rings, modules, you always have free and forgetful adjunction to any algebraic category. Here by algebraic I mean finitary algebras, and all the axioms are of the form that, like associativity, some identities hold for all elements, yeah, not the category of fields. Yeah, that doesn't fit into this bill. But for any such category, you will have an adjunction, so adjunction gives rise to a monad. Okay, and that if you construct this Eilenberg-Moore category associated with that particular monad, then you will get something equivalent to the original category. And this is what we mean by the adjunction is monadic. Okay, so the free forgetful adjunction to any category of algebras, any algebraic category, that's a monadic adjunction. I haven't defined it yet, but I will define it next time. Okay, so all algebra can be done just using monads. So just simple monoids in an appropriate category. Monads are monoids, right? Monads are monoids in the functor category. And its motivation came from homological algebra, where people were trying to study comonads. So comonad, as in like comonad has this data reversed. So it will have one one endofunctor obviously, then one natural transformation from T to identity. And so in that case, we'll of course use the co-unit. I mean, we asked the same question. What was our original question? That this is an adjunction. Without referring to category D, how much of the adjunction can we describe? If we change our question to without referring to category C, how much of our adjunction we can describe, then we'll get epsilon, and simultaneously we'll have a co-multiplication. It will be a map from T to TT. Okay, co-multiplication. So that is what we do. I mean, usually the duplication map is T, co-multiplication. On words, you start with a word and then you duplicate that word. That's a co-multiplication. And it satisfies the dual properties of a monoid. Okay, so here we are trying to understand all the algebras from the perspective of one simple example, monoids, but not ordinary monoids, set theoretic monoids, but monoids taken in the category of functors, endofunctors. So every algebraic category will be like this. So that's why this is an important concept. Okay, this is like the universal algebra construction. Okay, so now I can like say that, yeah, I mean the category.
So 0.6b f of m dot a equals m dot fa.
Oh, okay. Yes, okay, fine. I made a mistake there, m dot fa. Yes, so the category CT is called the category of T algebras. Okay, now our answer is not yet done. Yeah, I mean this is just Eilenberg and Moore's construction. But what was the question? That does every monad come from an adjunction? Now we still have to describe some adjunction and put on your thinking caps and tell me how we can define some kind of adjunction. So we have to do this. Yeah, Ft over here, and on the other hand we will have Gt, and then this should be an adjunction. We have to verify all these things. First, try to describe to me what is Ft of an object A.
The initial object.
Initial algebra, that doesn't make sense. I mean, what was our motivation? Free algebra, huh?
First have to give a T, right?
Yes, we have to give an object and a morphism. Yeah, algebra is a pair, A comma alpha. So what is that? I'm giving an object. The only thing I can do is TA. because TA obviously has an action, and TTA to TA, this should be my arrow, and what should be the arrow? Tell me. Exactly, mu sub A. Because I know this. Yeah, that is FT. It's the free algebra functor. And on the other hand, what will I do? If I have GT and acting on A alpha, then I will forget about the algebra part and I will remember the underlying object. So GT of A alpha is A. Okay. We still have to check something. So FT of A is a T algebra thanks to diagrams 1 and 3. Okay, now I have to show you something. So what do we want? We want that 4 and 5 are satisfied. Okay, but look at 4 and 5 in the special case. It's A to TA to A. Yeah, but our A is TA. So TA to TTA to TA. And vertically we are going to take mu A, and horizontally we are going to take eta sub t, which is precisely diagram 1. And similarly, look at diagram 3. Yeah, diagram 3 is exactly what we need for diagram 5. Yeah, we are just replacing A by TA. So all the things are happening internally, and alpha is mu. So
What happened to the triangle 2?
triangle 2 we haven't used here. We just need that 1 dot A is equal to A.
What about A dot 1 being equal to
Do you ever define A dot 1 in monoid action or group action?
No, but
No.
why is that information being
Because it's just the left action.
okay.
Yeah, so it's just a left action, so we don't need that. So FT of A is a T algebra thanks to 1 and 3. Yeah, I mean 4 and 5 are just 1 and 3. Okay, finally, what is the endofunctor induced by GTFT? So GTFT, you can see that is actually equal to T from C to C, because you start with an object A, you go to TA comma mu A and you forget about mu A, so you return to just TA. So GTFT is actually T. Okay. Then what is the unit of this adjunction? I mean, we haven't checked anything here, but define eta from 1C to T to be the given natural transformation. I mean, given as part of, yeah, I mean, given as part of T, because T already contains T eta mu. Okay. Finally, we also need epsilon. So epsilon we want to define. So epsilon should be from where to where? Tell me. From FT GT to 1 sub CT. Okay, we haven't yet verified that it is an adjunction. We are in the process of verifying that. Okay, so we have to define this particular epsilon given by the data. So any natural transformation is given by the data, that epsilon sub A comma alpha, this is happening from FTGT A to A alpha, sorry, to A alpha. We have to define it. What should be our definition? What is this? I mean, first of all, let's try to simplify this. You take A alpha, you forget alpha. This will be TA mu A. Okay, so from TA mu A to A alpha, can you define something obviously? Yes. Yeah, so this is alpha. Why would alpha work, TA mu A? Yes. Yeah, so is indeed a natural transformation thanks to 5. Okay, please observe that 5 is nothing but 6 in the special case that B beta is A alpha and A alpha is TA mu A. Okay. Good. So far so good. So the is indeed a natural transformation. So now we have got data of 2 functors, 2 categories, 2 functors and 2 natural transformations. How do we verify, given this data, that it is an adjunction? Triangular identities. Yes, we will verify. We verify triangular identities. To complete the verification of the adjunction. Okay, so what are triangular identities? I am not going to write it in the functorial form. I will directly write it in like by applying those functors to the to objects. Yeah, so FTA to FT GT FTA, and here I have FTA. Obviously this is 1 sub FTA, nothing is happening over here. Then this is epsilon sub FTA, and horizontally we have F eta A. Okay, why does this diagram commute? I mean, this is Ft eta A. You have got all the diagrams on your screen. Maybe I will write down the second one while you are thinking. So GTA alpha, GTA alpha again, then GT, FT, GT, A alpha, and this is diagram 4. First one is 4. Let us verify everything together. Okay, perhaps we should simplify certain arrows and then only we will understand what's really going on, if we can. So what is epsilon sub A alpha? We defined it to be alpha. Okay, so GT alpha, this is GT alpha. And eta sub this, okay, that we understand. So what is GTA alpha? A. So this is mapping from A to A. Yeah, I mean, maybe I should write it A to A. This is 1 sub A. Then this is GT of A alpha is A. FT of that is TA mu A, and TA mu A we forget mu A. So we will get TA. And this is just GT of alpha. Well, what do we remember over here? Yeah, just alpha, and eta sub GT A alpha, so eta sub A. So which diagram is this? This is 4, okay. So this is just 4, and what is this? TA comma mu A. Yeah, then this is TA comma mu A. And this is TTA, I suppose. TTA comma mu sub mu TA. Okay. And this is 1 sub TA. This is just 1 sub TA mu A. Okay, what is the vertical map? Epsilon of TA comma mu A. That is just mu A. And horizontally, Ft of eta sub A. So GT alpha. That is GT alpha is just alpha. What is Ft? Okay, did we describe Ft on maps? Yeah, okay. So maybe I forgot to mention that. I should do that, like Ft on A comma alpha, A to B. Yeah, this is something I forgot, so I should mention that. Is just TF. Okay, Ft is just TF, and what is GT? GT of A alpha to B beta, and this map F, I think it is just F. Don't need anything else. Okay, so GT composed with alpha, well, it won't do anything. That's why we get this GT alpha is actually just alpha. And the vertical one was correct in this first diagram. We just have to look at Ft of Ft composed with eta sub A. Yes, T eta sub A. This is nothing but just diagram 2, T eta sub A. Please look at diagram 2. Yeah, that's precisely what we are writing. At object A. So we verify these triangular identities. So this is 2 and the other one is 4, and therefore everything works. So triangular identity verification tells us that this is actually an adjunction. You are still confused.
How did diagram 2 come into the picture?
Because diagram 2 is precisely TA. Yeah, this is TA.
Yeah,
Okay, even though there are algebra morphisms, you just have to verify the underlying commutativity of maps, and that is just diagram 2. You don't have to worry about the algebra structure because it already behaves well. So you just have to remember how the underlying morphisms work in category C. So verifying this diagram is nothing but verifying some diagram in category C itself, and that is precisely 2. Okay, so this is the complete, no, we are yet to do one more little thing to complete the verification. So finally, yeah, so if you remember, we said that given an adjunction, the monoid action the multiplication of the monoid that was given by, see here, G epsilon sub F. We have to verify that it is indeed what we got. Well, let's try. What is it? Ft of A is Ta comma mu A, right? So this is Gt, and epsilon sub A comma alpha is just alpha. So therefore Gt mu A, but Gt doesn't change the morphism, so this is indeed mu A. So that's our verification. Okay, we wanted that the monad multiplication that was given, we can recover it from this adjunction as well. So we verified. So finally this Gt is in Gt epsilon sub Ft is indeed just mu. Okay, so this completes the verification. Therefore Ft Gt induces T. Think about the genius of Eilenberg and Moore, who came up with this construction that every free algebra construction is now just a single monad. Okay. Then, of course, there is another construction, and Kleisli was apparently a minimalist. So let me write that. So Kleisli's minimalistic approach. Okay, so he constructed, so assuming, yeah, I mean, I will just give you the motivation first. So assuming that C is locally small, and that F is essentially surjective. So that we can replace the category D. Yeah, I mean, oh, okay. I think I should say something more. Given an adjunction and assuming that C and D are locally small and F is essentially surjective, so that we can replace F by its full subcategory. So that we can replace D by the full subcategory. Consisting of objects of the form Fa. Okay, so if such a situation happens, then what can we do? Yeah, I mean, it was just an observation which led to this entire construction. We have, yeah, I mean, see this, D, Fa, Fb. Every object looks like this, Fa, Fb, and we are given an adjunction. So what does that adjunction say? That this home set should be in bijection with C what? C, A comma? No. A comma, GFB. GFB is nothing but TB. Okay, so this observation is the crucial thing. in Kleisli's construction. He says that if at all F is essentially surjective, then we have this identity. So what should D be? I mean, he's trying to understand D in terms of C using this bijection. Okay, so let's do this now. So let us define. So the objects. So Kleisli defines this category. So Kleisli's category CT, where T is taken here at the bottom, it's a subscript. What are its objects? Objects are same as objects of C. Okay, no change at all. But morphisms are interesting. So morphism from A to B, you define it to be C from A to TB. CT is now playing the role of D in the above expression. So CT of A comma B is C of A comma TB. However, now as soon as we say this, then there are so many things to verify. How do we compose? Yeah, composition goes from A, if you are given map from A to B and B to C, how do we compose? Okay, so I have to describe all those things to you. Okay, so I'm going to do this. So A and zigzag morphism in CT is A to TB. I can very easily use a different color, but because you don't have different colors, I will not. I will just call it a zigzag morphism. So this morphism is nothing but simply a morphism from A to TB. Okay. What is the identity? Identity should be a map from A to A, zigzag morphism from A to A. So it should be a map from A to TA in the original category. What is it? Eta. Okay. So A to A is A to TA, which is eta. Then I have to describe composition. So composition of two zigzag morphisms in CT. Well, you obviously have a morphism from A to TB, which is F. Okay, from TB, obviously, you only know what B to C is. So you have to apply T on that, and you will go to G is from B to TC. So this is TTC, and this is our TG, not G, it's TG. And then finally from TTC to TC we can come back, because we always have to come back to just one application of T, and that's by mu C. So Kleisli was using all the data, yeah, that was given in the definition itself. Okay. So, well, obviously, once the operation is such a weird operation, we have to verify, yes, whether composition is associative. So, associativity. So, what should we start with? Well, I will say this, A to B, this is F, then you have B to C, which is G, and C to D, which is H. Okay. So what is it? Well, is you have A, then TB, obviously. Perhaps I should specify what I am doing first. I am doing this composition first. Yeah, A to TB, and then I have TG to TTC, and then I have okay, mu C. I am purposely writing this morphism vertically, although I am just taking composition. Then from TC, I have to use H. So what will H do? TH to TTD, very good, and TTD to TD by mu D. Okay. Now I have designed the diagram in such a way that everything has to happen properly. What should this be? Tell me. I can complete this diagram. This will be TTH to TTTD. Right? And then I will take the morphism vertically. What is that? Mu sub TD. This diagram commutes, this square commutes because mu is a natural transformation. Okay? And observe what is happening here. Like I will underline using a different color, of course. B, TC, TTD, TD, and G and TH. Just look at this red part. That red part is nothing but the composition of G with H. And I have applied T on this H composed with G. And then finally I am doing mu D. So everything works out fine. So this diagram is associativity. Okay? Good. Identity, of course, we have to verify. So A to 1A and then F. Okay, what is this diagram? You take A to eta A, this is to TA. Okay, so I'll just write it vertically, and then this is mu B to TB. Can I complete the first square? This is TF, yeah? So here I can do F, and F I can do to TF, and then TB to TTB, what will I have? Eta sub TB. Now eta sub TB and mu B, they compose to give you the horizontal composition is just identity, thanks to which diagram? Diagram 1. Yeah, so this is actually using diagram 1, this is actually just F. Okay, this is one-sided identity. The other side identity is also interesting. So that is B. I mean, that's easy actually. 1 sub B. What is this composition? It's just A to TB. Yeah. And this is F. Then from TB to TTB, we will have T eta. And TTB, mu B will come back to TB, and this particular, I mean, this composition is obviously 1 on TB thanks to diagram 2. So using diagrams 1 and 2, we can verify that this is indeed a composition. So minimalistic approach, you understand the idea. Don't look elsewhere. Just work with whatever you have got. Yeah, so very beautiful solution. Unfortunately, Kleisli never got the recognition. Like even his category did not get enough recognition. Eilenberg-Moore has been used in past 50 years quite a lot, but Kleisli did not get that recognition. But I was happy that to see that there was one student working with me earlier, and he found out a thesis, PhD thesis, I think from Oxford or Queen Mary University of London, which was using Kleisli category in game theory. Okay, so categorical approach to game theory. Right, so maybe I should remind you what we are trying to do. We have C, we have CT, then FT, and we have GT. Okay, so FT we have to describe. What should be FT on objects? Same object. Yeah, you don't change anything. Okay, so, so FT of A is just A, and FT of A to B, yeah, an ordinary morphism, what will you map it to? It should go from A to TB. Yeah, then only we can say it's a morphism from. Exactly. There is the, yeah, as is everything in category theory, if it exists, then it is obvious. So eta B composed with F. This is our FT. Okay, then perhaps you should also verify what happens. Like, is FT really a functor? So FT of identity is actually eta B, eta A. And eta A is the identity in CT. Okay, then FT of composition, well, I will leave it as an exercise. FT preserves compositions. Please do that. Huh? Or maybe for the sake of completeness, let me do that. So FTG composed with FTF. Okay, what will this be? We'll have A, 2. First of all, what should be the first composition? A to B, then to TB. Right, so that is just F, this is eta B. Then we have to compose in category CT. What does that mean? You take the same thing but by applying T to everything. So this will be TG from TB to TC, and then T eta C to TT C, and then finally we will have TC, and this will be mu C. That's our composition. Okay, then observe that from here we can change it. We can find this commutative square over here. What should I put here? Just C. And here I will have G, and what will I have here? Eta sub C. Okay. Then tell me, what is mu C composed with T eta C? For this particular diagram, this is 1 sub Tc. This is diagram 2. Okay. Then this is GF composed with eta C. Can you see that? GF composed with eta C at the bottom. Follow this, and then rest is identity, and that is precisely FT of GF. Okay, so we have verified that this is indeed a functor. Okay, so far so good. However, yeah, now the right adjoint that we want to find is not easy to find. Huh? I mean, if you look at this construction, then where will you send an object to? If you send it to itself, see, remember, I mean, we are not Kleisli, so we are not trying to look for an answer. Yeah, we already know that it works. So obviously what should happen? An object should get mapped to T of itself, because then only it will induce the same monad. GT of FT should be T. Okay, so FT is just sending A to A. So ultimately it should send A to TA. But whenever we do not know how to proceed, yeah, then we usually take help of some result that we have proven. So how do we verify that a given functor has a right adjoint? We obviously, yeah, no. To obtain the right adjoint, or obtain, like, to ensure the existence of the right adjoint, GT of FT, we need to understand, we need to investigate the arrow category FT arrow A for any A in object of CT or C. CT. Okay. Normally, remember, I mean, earlier we said that G has a left adjoint if and only if the arrow category A arrow G has an initial object, to consider left adjoint, the arrow category A arrow G, whereas here we are switching their positions. So FT arrow A has a terminal object. So that's what we have to verify, that this particular category has a terminal object. Okay, we'll quickly do that. Okay, so what are the objects of the arrow category? Well, they are B comma F, where F is a morphism from B, is a zigzag morphism from B to A in CT. I mean, whenever I am writing B to A, I actually mean FT B to, maybe I should specify, where F is a morphism from FTB equal to B to A. Okay. So which means it is a morphism from B to TA. Okay. And a morphism in this category is, okay, so BF to B prime F prime, and this is just some G, yeah, where G is a morphism from B to B prime in C. It's not a zigzag morphism. Okay, so now FT of B to FT of B prime, and here we should have FT of G, okay, which should be a wiggly morphism, and this is also F, and this is A, and this is F prime, a wiggly morphism. Okay. Now, okay, can we simplify this diagram? Yeah, that's what we have to do. ft of b is just b. Yeah, so this is b and this is b prime. What is ft of g?
G composed, eta of B prime composed with G.
Okay, so let us write that down. Yeah, so this is the wiggly morphism, but so let's. So b to b prime, sorry. ftg and f prime to a. Okay, this composition is equal to, you have to first take b to b prime, and that is g, then you have to do eta sub b, and that is 2 tb, eta sub b prime to tb prime, and then we have to take f prime. Yeah, but f prime is a morphism from b prime to ta. Okay, so b prime to ta. So you have to first take t of f prime to tta and followed by mu sub a. Okay. Now, obviously you can see there is some diagram that we have to use. This is eta sub, this can go to ta and ta to, this will be eta sub ta, and this will be f prime. Okay, and then eta sub ta followed by mu sub a, that is 1 sub ta, and this is property 2, 1. I think eta sub t is 1. So diagram 1, make sure that whatever we have is just f prime composed with b. Okay, so this is b to b prime to ta. Okay, so therefore let me call this particular diagram star. So therefore star commutes if and only if I start with this b and then f is from b to ta, that is f, then this is g which is to b prime, and this is f prime from b prime to ta. This commutes. Okay, so this diagram commutes, this wiggly diagram in CT, yeah, is in CT, if and only if this commutes in C. So therefore, what did we conclude? The most important thing that we observe, I think we are, yes, we can say that. So this arrow category is in fact isomorphic to the category identity functor arrow ta, which is just the slice category. Yeah, the slice category. And do you remember anything about terminal objects in slice categories? Identity morphism on that object is the terminal object. And yeah, this has, so 1 sub ta, ta comma 1 sub ta is the terminal object. Okay, so you actually, we can use that theorem to conclude that this indeed has a right adjoint. Okay, now I am going to say, we have already done enough. So follow the proof of, whatever that result was, of the result follow the proof of the result to obtain the right adjoint gt of ft given by, okay, gt of A equal to TA and gt of A wiggly arrow F is equal to, well, this is actually a morphism from A to TB, yeah. So F is a morphism from A to TB, so I should do TF and then follow it up with mu B. Okay, so this is our GT. Okay, so follow, now that we have shown that this arrow category is the slice category, isomorphic to the slice category, which always has a terminal object. So using the dual of that result, or you actually follow the proof of that result to obtain the right adjoint GT of FT, where, I mean, if you follow the proof properly, you will know that GT of A is TA and GT of this curved arrow, this wiggly arrow from A to B, will be this composition TA to TTB TF and followed by mu B, yeah, so that we land in TB itself. Okay, now there are some little bit more things to verify before we can finish discussing this Kleisli construction. So epsilon A, yeah, from TA to A is in fact just, yeah, I mean epsilon A, where does it happen? It happens in the CT category. So epsilon A is just the identity map on TA. This also you can verify very easily. Eta from A to TA, this is happening in category C, is the prescribed TA, prescribed eta, prescribed as in the one that is given as part of the data of the monad, and GTFT of A is equal to TA, which means we are recovering the endofunctor correctly, yeah. And finally, yeah, I mean together with the action on the morphisms, that also we have to say. So if you start with an ordinary morphism in category C, then you will actually recover what is FT of F. Do you remember that? We took A to B, F followed by eta B. Yeah, this was the actual morphism which went to TB, and then now we are supposed to take its GT. So this is the wiggly morphism from A to B. So its GT is going to be TA to TB to TTB. I mean, I just took the same thing. I just applied T on it. So this is TF, then T eta B, and then followed by mu B. But you already know this diagram is just going to be 1 sub TB thanks to diagram 2. So therefore this is just TA to TB. Okay, so GTFT acts on objects and morphisms the way we want it to. So it is actually the endofunctor which was given as part of the data of our monad. Okay, one final thing that to see is this. What is GT? What is the monad induced by it? Yeah, what is the multiplication induced by this adjunction? So we have to verify that. So FT sub A. Okay. What is this? Well, this is TTA. Then T of 1 sub A. 1 sub TA, sorry. 1 sub TA. To TTA. And then you apply the multiplication. I mean, of course, there is a gap here. Apply the multiplication over here mu A. Well, this is, oh, I think I made a, yeah, this is in fact just equal to mu sub A. Yes. Yes, so mu sub A is precisely what we wanted to obtain. So the multiplication given by this particular adjunction, the Kleisli adjunction, is also mu. So we have verified literally every single thing. Yes. And therefore, what did we show so far? That we found this particular adjunction, yeah, FTGT, which induces the same monad. So if you remember, what was our original question? That does every monad come from an adjunction? And there were two independent answers by Eilenberg-Moore and Kleisli. Both of them gave positive answers in 1965, and we saw both these answers. Yeah, there are certain things I have left for you to check, but anyway, I am not going to cover all the proofs now. Any questions so far?